This is our ME 475 final project. We did a bicycle frame analysis. I'm Basil Thurston.
And I'm James Hargrove. This analysis, as we mentioned before, focuses on the stresses and deformations a bike frame might experience if it goes off of a jump. The model is based on a basic road bike with a reinforced rim. This makes it a more simplistic model because of the fact that these rims cause the frame to basically have fixed conditions on both ends, because there's no real complex suspension system that needed to be modeled. Transient analysis was done to show what the bike will experience over the course of 4 seconds as it first hits the ground after a jump.
This bike frame was modeled similar to the Lab Exercise 2, which was a Baja car. Given that these beams were actually circular beams rather than the rectangular beams, it didn't matter the orientation of them. There were 5 different cross sections for each of these beams. They were modeled from coordinates points that were grid lines, and then cross sections were applied. After that, all the parts were made into one giant part file where it could be modeled and everything would be connected. The material properties used was steel. We were considering something like this being a steel frame because something that would be aluminum frame would have thicker cross-sectional areas, and we thought this would be best for the frame that we were using. The table shows you the cross-sections that we used on the model.
The boundary conditions used for this problem are, as I mentioned before, to simulate a bike going off a jump. So fixed supports were placed at the front and back of the frame to simulate the reinforced wheels, as they are more rigid and can be replaced instead of a complex suspension system. The load was then applied at the bottom joint, where the pedals would be and where a person would be standing. Usually when a person goes off a jump, they will be standing to absorb some of the force of the impact through their knees, so the load is only applied there and not up by where the seat would be. The load values were assumed to be the combined weight of the bike and the rider, which maxed out at around 950 kilograms. And due to the nature of this being a transient analysis, all the weight was first applied at the first time step and then lowered as the time went on to simulate the initial force of impact of the bike hitting the ground, and then that would be tapering off to simulate the normal conditions of riding.
The results show, as expected, that the stress and the deformation decreases as the load decreases. Failure is most likely to occur at the bottom joint, which was surprising. Not in fact because we didn't know that it was going to occur there, but we didn't know where it was going to occur, mainly because the different cross sections. Bike is already optimized because of all the different cross sections used. The crossbar isn't as large as the rear support, so it was kind of interesting to see where it would fail. And given the actual loads that we put on it, we knew that it wasn't going to fail because they're very minimum deformation that occurs. And this is explainable too because of the structural shape of the bike. It is basically made from 2 triangles, which are the strongest structural shapes that are used in most civil engineering cases. So here are some of our results. This one will be deformation, and as you can see that the most deformation are going to happen around the joints where the seat post is on the top and the bottom. And like I said before, the failure would actually occur at the bottom joint where the bottom bracket would be located. And this is probably just because this is where the load is directly applied, and this is where the rider's weight is situated.
Similar to the Baja car that we analyzed earlier in class, we also determined the direct stress that was experienced on the bike frame. So the direct stress is the stress component due to axial loading. And as can be seen, the picture on the left is when the largest load was applied, and the picture on the right is when the lowest load was applied. The direct stress of 8.62 to the 6th is actually extremely small. It's about 8 megapascals, and that is not anywhere close to failure for the material used for this project. So the direct stress experienced obviously is quite small and can basically be negligible. We also determined the maximum combined stress. This stress is a combination of the direct stress and the maximum bending stress. So similar to the direct stress, this is not large enough to cause failure in this bike. We did determine what load would cause the failure, and that's about 100 times what is currently experienced. So this bike is clearly safe and not going to fail under the current conditions and under normal operating conditions. Any questions?